What if the universe doesn't have a beginning or an end? Imagine a cosmos that eternally cycles through periods of expansion and contraction. This is the captivating idea behind bouncing cosmology, a theory suggesting our universe might be just one chapter in an endless series of cosmic epochs. This challenges the traditional Big Bang model, offering an alternative view of our universe's origins. Could we be living in the aftermath of a cosmic bounce, a universe reborn from the ashes of a previous cycle? To understand bouncing cosmology, we must first grasp the prevailing theory of the universe's beginnings, the Big Bang. This theory has been the cornerstone of cosmology for decades, providing a framework for understanding the origin and evolution of the cosmos. About 13.8 billion years ago, our universe emerged from an incredibly hot, dense state, often described as a singularity. This singularity contained all the mass and energy of the universe in a space smaller than an atom. In a fraction of a second, this singularity began to expand and cool, a process known as cosmic inflation. Over the next few billion years, the universe continued to expand and cool, leading to the formation of galaxies, stars, and planets. This expansion continues today, evident in the redshift of distant galaxies. The redshift occurs because as galaxies move away from us, the light they emit stretches into longer, redder wavelengths. The Big Bang model has been incredibly successful in explaining numerous observations, such as the large-scale structure of the universe and the distribution of galaxies. It has also provided insights into the fundamental forces and particles that govern the cosmos. One of the most compelling pieces of evidence for the Big Bang is the cosmic microwave background radiation, a faint glow left over from the early universe. This radiation provides a snapshot of the universe when it was just 380,000 years old. Another key piece of evidence is the abundance of light elements, such as hydrogen, helium, and lithium, which were formed during the first few minutes of the universe's existence. These elements are found in the same proportions predicted by the Big Bang theory. However, the Big Bang theory leaves some questions unanswered, particularly about the universe's state before the Big Bang. What existed before this explosive event? Was there a previous universe, or did time itself begin with the Big Bang? These are some of the mysteries that scientists are still trying to unravel. Bouncing cosmology offers a different perspective. Instead of a singularity, a point of infinite density where the laws of physics break down, it proposes a bounce. In this scenario, the universe contracts until it reaches a tremendously dense but finite state. Instead of collapsing into a singularity, a repulsive force kicks in, triggering a new expansion, a bounce. This cycle of contraction and expansion could repeat indefinitely, making our universe just one iteration in an eternal cosmic dance. Several theoretical frameworks support bouncing cosmology. Loop quantum cosmology, a theory attempting to quantize space-time, suggests that at extremely small scales, space itself is quantized. It exists in discrete units. This granularity could prevent the universe from collapsing to a singularity, leading to a bounce. String theory, which posits that fundamental particles are tiny vibrating strings, also offers possibilities for a bouncing universe. In some string theory models, extra spatial dimensions could provide the repulsive force needed for a bounce. Section 5. Visualizing the bounce. Imagine a balloon deflating. This represents the contracting phase of a bouncing universe. As it shrinks, the balloon becomes increasingly dense, but instead of disappearing entirely, it suddenly reinflates. This reinflation is akin to the bounce, with the universe expanding once more. Of course, this is a highly simplified analogy. The actual dynamics of a bouncing universe are far more complex, involving interplay between gravity, quantum mechanics, and possibly other fundamental forces. Section 6. Echoes of a previous cycle. If our universe did indeed experience a bounce, there might be remnants of the previous cycle. This concept, known as the cyclic model, suggests that the universe undergoes endless cycles of expansion and contraction. Each cycle begins with a Big Bang, followed by a period of expansion, and eventually a contraction leading to a big crunch, which then triggers the next Big Bang. These remnants could manifest as anomalies in the cosmic microwave background radiation, the faint afterglow of the Big Bang. The cosmic microwave background radiation, or CMB, is a snapshot of the oldest light in our universe, dating back to about 380,000 years after the Big Bang. The CMB provides a wealth of information about the early universe, and any irregularities or anomalies in this radiation could potentially be clues to events that occurred in a previous cycle. Some physicists believe these anomalies could be bruises left over from collisions with other universes, or perhaps even interactions with parallel universes. The idea of a multiverse, where our universe is just one of many, opens up fascinating possibilities for what these anomalies could represent. Alternatively, these anomalies might be echoes of structures from the previous cycle. If the universe is indeed cyclic, then certain patterns or structures could be imprinted on the universe during each cycle, leaving behind faint traces that we can detect today. These signals, however, are faint and open to interpretation. The challenge lies in distinguishing between genuine signals from a previous cycle and noise from other cosmic events. Distinguishing between signals from a previous cycle and noise from other cosmic events remains a significant challenge. Scientists use sophisticated instruments and techniques to analyze the CMB and other cosmic data, searching for patterns that might indicate a previous cycle. Despite the difficulties, the quest to understand the origins and fate of our universe continues to drive scientific inquiry and exploration. Section 7. Challenges and controversies. Bouncing cosmology, while intriguing, is not without its critics. One major challenge is explaining the mechanism behind the bounce. What force could counteract gravity's relentless pull and trigger expansion? Another criticism revolves around the second law of thermodynamics, which states that entropy, a measure of disorder, always increases. A bouncing universe would need a way to reset entropy with each cycle, or else each subsequent universe would become increasingly disordered and short-lived. Section 8. The multiverse and beyond. Interestingly, bouncing cosmology intersects with other intriguing ideas in cosmology, such as the multiverse. Some models suggest that our universe might be just one of many, each with its own set of physical laws and constants. In a multiverse scenario, bounces could be relatively common, with universes constantly being born and reborn. The concept of a multiverse, however, remains speculative, and its connection to bouncing cosmology is still being explored. Section 9. A universe without end? The idea of a universe without beginning or end is captivating. It challenges our understanding of time and space, pushing the boundaries of what we know about existence itself. For centuries, humans have gazed at the stars, wondering about the nature of the cosmos. Is there a starting point, a moment of creation, or has the universe always been here in one form or another? It speaks to our innate desire to find patterns and order in the cosmos. The night sky, with its myriad of stars and galaxies, has always been a source of inspiration and mystery. Ancient civilizations built monuments aligned with celestial bodies, trying to decode the messages of the heavens. Today we use advanced telescopes and satellites, but the quest remains the same, to understand our place in the universe. While bouncing cosmology is still a developing theory, it offers a fresh perspective on some of the most fundamental questions about our universe. This theory suggests that the universe undergoes endless cycles of expansion and contraction, each cycle giving birth to a new universe. It's a radical departure from the traditional Big Bang theory, which posits a single moment of creation followed by continuous expansion. As we continue to probe the cosmos and refine our theories, we might find ourselves closer to understanding whether we live in a single, finite universe or one chapter in an endless cosmic cycle. The implications of such discoveries are profound, affecting not just our scientific understanding, but also our philosophical and existential perspectives. Are we part of an eternal sequence, or is there an ultimate end? The quest to unravel the universe's ultimate fate continues. With each new discovery, we peel back another layer of the cosmic mystery, bringing us one step closer to answering the age-old question: what is the true nature of the universe? Whether we find that it is infinite or finite, cyclical or linear, the journey of exploration and discovery is what drives us forward, ever curious, ever seeking.